The K-center problem, a fundamental optimization problem in machine learning, data mining, and communication networks, involves locating a small set of points in space that minimize the maximal distance from them to any other point. While extensively studied in centralized and parallel settings, this problem has not been thoroughly explored in traditional distributed settings, where the communication graph of a network defines the distance metric. This research initiates the study of the K-center problem in three canonical distributed settings: local, congest, and CLIQUE models, where the underlying metric is the graph's shortest path metric. Unlike previous studies which assume points and metric from a metric space, this work considers a graph representing a communication network, where the metric space is the graph metric on the graph itself. This distinction is crucial, as the K-center problem has significant applications in determining server placement within a network to minimize maximum delay, such as content distribution over the Internet. The K-center problem differs from related problems like the metric facility location problem, which aims to minimize the average distance from servers, and the online K-server problem, where points and servers can move in space. This research addresses the K-center problem in the local, congest, and CLIQUE models, deriving upper and lower bounds. Notably, prior work in these distributed models considered points in an arbitrary metric space, independent of the communication graph. This study is the first to explore the natural setting where the input graph represents both the network used for communication and the metric on which K-center is solved. The authors delve into the K-center problem in distributed models, focusing on the shortest path metric in unweighted graphs. In the local model, where nodes communicate by synchronously exchanging messages of unbounded size, they present a 2k plus e approximate solution to the K-center problem in O, k, e rounds, relying on the assumption of unique node IDs. However, reducing the approximation ratio below k1 requires omega n time, which is sufficient for nodes to aggregate the full network structure and find an exact solution. In the congest model, a restrictive variant of the local model with O, log n, bit message limits, the authors present a 2-approximation congest algorithm for the K-center problem running in O, kd, rounds. This algorithm simulates a centralized greedy approximation algorithm. However, they also prove that improving the approximation ratio to below 4/3, and hence finding an exact solution, requires omega n k rounds, even for graphs with a small diameter of 12. This lower bound proof involves a reduction to communication complexity with an added post-processing phase. Finally, the authors consider the congested CLIQUE model, which resembles the congest model but with all-to-all communication. The distributed K-center problem in the CLIQUE model is a fundamental challenge in distributed computing. It involves finding a set of at most k nodes that minimizes the maximum distance of any node to its nearest center. A congest algorithm with O, kd, rounds does not directly translate to an O, k, round CLIQUE algorithm due to differences in the communication network's diameter and the construction of BFS trees. This research presents a deterministic algorithm that finds a 2-approximate solution for the K-center problem in O, n⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ distributed graphs. If the exponent of the matrix multiplication problem, omega, is discovered to be 2, the time for distributed matrix multiplication algorithms and 2 approximation of K-center would be improved to O, n-e, for any e greater than 0, or even polylogarithmic. The authors extend a simple greedy algorithms approximation guarantee from a 2 approximation to a 2 alpha approximation when only a one-way, multiplicative alpha approximation of distances is known. This extension provides new insights into the centralized case of the K-center problem. Current techniques cannot establish lower bounds in the CLIQUE model, and any non-trivial lower bound would imply circuit complexity lower bounds, solving a long-standing open problem. The paper concludes by discussing the K-center problem, its computational models, and the importance of understanding distributed algorithms for solving this problem efficiently. In the realm of distributed computing, this section delves into various models for distributed algorithms and their applications in solving the K-center problem. It commences by introducing the local model, which enables nodes to communicate with their neighbors and update their local state based on received messages. This model is characterized by unbounded message sizes and an equivalence to having each node decide based on its distance or neighborhood. The CONGEST model is then presented, where nodes are limited to sending lone bit messages to their neighbors in each round. This model allows for primitives such as constructing a BFS tree from a node, and can be extended to multiple BFS trees or trees of bounded depth. The CLIQUE model is also discussed, where nodes can send lone bit messages to all other nodes in the graph, enabling tasks like redistributing inputs in constant time and computing all pairs' shortest paths in sublinear time. The paper also delves into communication complexity, particularly the two-party set disjointness problem. In this problem, two players, Alice and Bob, receive LBIT strings and must communicate to determine if the sets represented by these strings are disjoint. The communication complexity of a protocol is defined as the maximal number of bits exchanged during its execution, with deterministic and randomized complexities differentiated based on the use of random bits. A lower bound of omega, L, for the disjointness problem is established, applicable to both deterministic and randomized algorithms. Finally, the section concludes with a discussion on related work, including traditional distributed computing models and the metric facility location problem in distributed settings. In the context of distributed computing models, the k-center problem in the local model is addressed through a deterministic O-K-E round algorithm, yielding a 2 plus e k approximate solution, as stated in Lemma 1. This algorithm initiates with the construction of a BFS tree of depth tk, where t is defined as 2 plus 4 e. After tk rounds, nodes report back up the tree if the tree construction algorithm terminated in all its branches or not. If it terminated, the maximum diameter d is at most tk, and in another tk rounds, node 1 can aggregate all the graph structure and find an optimal solution. Conversely, if the tree construction did not terminate, node 1 becomes the only center. This work builds upon related computational models and previous studies on the k-center problem. Bandyopadhyay et al. 2. investigated the k-center problem, along with the uncapacitated facility location and k-median problems, in the k-machine model, which is closely related to the CLIQUE model. Their work implies a randomized 2 plus e approximation O polylog n time k-center algorithm in the CLIQUE model. In contrast, the metric facility location problem has garnered more attention in distributed settings. For instance, Briest et al. 4. studied metric facility location in the CONGEST model, focusing on a bipartite graph with facilities and clients. Gayweiler et al. 14. presented a 3-round randomized algorithm that gives a constant approximation factor for metric facility location in a model resembling the CLIQUE, based on the method of Metu and Plaxton, 24. Inamdar et al. 18. studied metric facility location in the CLIQUE, MPC, and K-machine models, and gave an O-1 approximation algorithm using a Metu-Plaxton style algorithm, improving upon earlier works on metric facility location in the CLIQUE model, 3.16. This paper presents a 2 plus epsilon k-approximation algorithm for the k-center problem in the local model, alongside a lower bound on the achievable approximation ratio by any Tround algorithm in the same model. The algorithm leverages local computation to find an optimal solution, which can be replaced with a 2 approximation computed greedily. The proposed algorithm initiates with an initial value of t equals 2 plus 4 epsilon and performs a breadth-first search from node v1 for tk rounds. If all branches terminate within these rounds, the algorithm aggregates the graph to v1, computes an optimal solution locally, and disseminates this solution on the BFS tree. Otherwise, only v1 marks itself as a center. The algorithm's approximation ratio is shown to be at most 2 plus epsilon k, leveraging the fact that the eccentricity of node 1 is at most d, where d represents the largest distance between two nodes in the graph. A lower bound for the k-center problem in the local model is also established, applicable to both standard and bicriteria algorithms. Specifically, any Tround algorithm cannot achieve an approximation ratio better than kk squared plus k, beta k1, 2t plus 1, n plus k, where n greater than 2 beta kt is the size of the graph and beta is greater than or equal to 1. In the typical case, where k is a constant, this implies that achieving an approximation ratio better than k1 requires linear time. The proof of this lower bound involves constructing a communication graph as a cycle and executing the algorithm on it. By concatenating information segments gathered by each node and adding leftover nodes, a new cycle is created, demonstrating the lower bound on the approximation ratio. The authors present a proof for Theorem 1, which pertains to the k-center problem, demonstrating that algorithm A finds an approximate, bicriteria solution with an approximation ratio of at least k squared plus k, beta k1, 2t plus 1, n plus k. The proof begins by assuming algorithm A reports k is less than or equal to beta k centers for a cycle C of length n, with nodes labeled in a clockwise order. The centers returned by A are denoted as C1, Ck, in a clockwise order. Since n greater than 2 knots, there exist at least 2 consecutive centers with a distance greater than 2t. A new cycle C is constructed by rearranging the nodes of C, defining segments C equals by A of C, where each segment is centered around C and has a length of 2t plus 1 nodes. The segments may overlap, and their definitions are adjusted accordingly. The authors show that the solution A finds for C has the same centers as those found for C, namely C1, Ck, because the distanset neighborhood for any node C is the same in both C, and therefore, each node C makes the same decisions. The construction of C is illustrated in Figure 1, demonstrating how the segments C are concatenated to form C. The proof relies on the assumption that n greater than 2 knots and the existence of at least 2 consecutive centers with a distance greater than 2t. The author's construction of C allows them to bound the approximation ratio of A's solution, highlighting the limitations of A in solving the k-center problem. The authors analyze the approximation ratio of their algorithm, focusing on the clockwise path from C plus 1 to C asterisk operator in C. They demonstrate that this path contains at most k, 2t plus 1, plus 2t plus 2 nodes, implying that the distance from C plus 1 to C asterisk operator in C, in the anti-clockwise order is at least n, k, 1, 2t plus 1. Consequently, there exists a node in the anti-clockwise path from C plus 1 to C asterisk operator in C, with a distance to the nearest center of at least n, k, 1, 2t plus 1, 2. Comparing this to the optimal solution, where OPTK is less than or equal to nk, 2k, yields an approximation ratio of at least n, k, 1, 2t plus 1, 2, nk, 2k, is greater than or equal to n, k, 1, 2t plus 1, nk plus 2k, equals k squared plus k, 1, 2t plus 1, n plus k. The authors then present a 2 approximation in the CONGEST model, achievable in O, kd, rounds, where d is the diameter of the underlying graph. Algorithm 2 is proposed, which involves finding the node vmin with minimum id, performing a breadth-first search, BFS, from all nodes in S, and marking each node in S as a center. The algorithm iterates k1 times, with each iteration comprising a BFS from all nodes in S and the addition of the furthest node from S to S. Notably, the assumption of node ids being in 1, n, is not necessary, and assuming they are taken from 1, poly, n, suffices. A deterministic 2 approximation algorithm for the k-center problem in the CONGEST model is developed, requiring O, kd, communication rounds. This algorithm employs a greedy approach, similar to Gonzalez's method, which is known to have a 2 approximation ratio. The algorithm operates by iteratively selecting nodes with maximum distance to the current set of centers, S, until k nodes are chosen. A lower bound on the number of communication rounds is also presented for any algorithm achieving an approximation ratio better than 4/3 for the k-center problem in the CONGEST model. This lower bound is demonstrated using a graph construction, Gx, Y, introduced by Abood, Sensor Hillel, Khoury, and Paz. This graph consists of various node sets, designed such that the optimal solution for the one-center problem, OP1, satisfies OP1 equals 4 if and only if two input strings x and y are disjoint. By simulating a one-center algorithm and finding the distance from the chosen center to all other nodes, Alice and Bob can determine if X and Y are disjoint. If the algorithm is too fast, Alice and Bob can simulate it with too little communication, contradicting the communication complexity lower bound for disjointness. The lower bound for the one-center problem is then extended to the k-center problem for a general K by applying the same graph construction and principles to multiple sets of nodes in the graph. The paper concludes that any algorithm with an approximation ratio better than 4/3 must require at least a certain number of communication rounds, providing a lower bound on the complexity of solving the k-center problem in the CONGEST model. This result highlights the fundamental limits of solving the k-center problem in this model, emphasizing the importance of efficient algorithms with optimal approximation ratios. The graph Gx, Y, as depicted in Figure 2, is a complex structure comprising nodes and edges that connect them. Nodes A_I and B_I are linked to the binary representation of I in sets F_A and T_A, and similarly for B, edges connect C_A to all nodes in A and C_B to all nodes in B, as well as edges from C_A and C_B to nodes in F_A, T_A, F_B, and T_B. Furthermore, edges connect nodes in F_A, T_A, F_B, and T_B, and nodes W_0, W_1, and W_2 are connected to nodes in A and to each other. Claim 1 states that for every node U not in A, the eccentricity, or maximum distance to any other node, is at least 4. Additionally, for every node A_I in A and every node U not in B_I, C_B, the distance between A_I and U is at most 3. To prove this claim, we first show that the distance from W_2 to any node not in A are W_0, W_1, W_2 is at least 4, and then demonstrate that the distance from C_B to any node in W_0, W_1, W_2 is also at least 4. The second part of the claim is proven by observing that the distance between A_I and any node not in B or C_B is clearly at most 3, and that for any j not equal to I, there exists an h such that the hth bit in the binary representation of I and j differs, allowing for a path of length at most 3 between A_I and B_j. For any strings x and y, if the distance between any two nodes I and bj is at most 3, then a rigorous proof in Claim 4 of Reference 1 ensures the second part of the claim holds. The concept of disjoint strings is introduced, where x and y are not disjoint if there exists an index I such that x, I, equals y, I, equals 1, and otherwise, they are disjoint. Lemma 3 states that if x and y are disjoint, then the optimal one-center solution for the graph Gx, y is 4, and otherwise, it is 3. The proof involves considering two cases: when x and y are disjoint, and when they are not disjoint. In the former case, it is shown that the optimal one-center solution is at least 4, and since all nodes are within distance 4 of A0, the optimal solution is exactly 4. In the latter case, it is shown that the eccentricity of I is 3, and therefore, the optimal solution is 3. Theorem 3 states that any CONGEST algorithm that returns an alpha approximation for the one-center problem with alpha less than 4/3, even randomized, must take omega n log 2n rounds to complete. The proof involves assuming the existence of a faster algorithm and simulating it on the graph Gx, y. Alice and Bob, who are in charge of the nodes on the left and right sides of the graph, respectively, simulate the algorithm and exchange bits to simulate the messages between nodes. If the output of the algorithm is a node not in A, they return 1 for the disjointness problem. If it is some node I element of A, they exchange the bits x, I, and y, I, and return 0 for the disjointness problem if and only if x, I, equals y, I, equals 1. The correctness of this approach is shown by considering two cases: when Alice and Bob return 1 because of a center U not an element A, and when they return 1 because of a center I element of A. In both cases, it is shown that if the sets were not disjoint, lemma 3 guarantees that the optimal one-center solution is 3, leading to a contradiction. Finally, the complexity of the approach is analyzed, showing that Alice and Bob exchange T log 2n bits to simulate the rounds, where T is the number of rounds used by the algorithm. The paper delves into the lower bound for the K-center problem in distributed algorithms, particularly focusing on CONGEST algorithms. It introduces a graph GKX, Y, which is composed of K copies of a graph GX, Y, where all copies share a node W2. The authors prove that any CONGEST algorithm aiming to achieve an alpha approximation for the K-center problem with alpha less than 4/3 must take omega n, K2 log 2n, rounds to complete. The key argument begins by establishing claim 2, which states that in any alpha approximate solution for the K-center problem of GKX, Y, alpha less than 3/2, exactly one center is chosen from each copy. This claim is supported by lemma 3, which ensures that each copy can choose a center and achieve a solution with distance at most 4 from each node to a center, while the optimal solution, OPTK, is at most 4. Theorem 4 then extends the lower bound for the K-center problem. The proof assumes a faster algorithm than the theorem statement and simulates this algorithm for L input bits, where L equals theta, n, k. Alice and Bob get an output in the form of K-center nodes and simulate the algorithm for L input bits. They exchange x, I, y, I, and answer 0 for the disjointness problem only if x, I, equals y, I, equals 1 for at least one such I. The correctness of the algorithm is ensured by claim 2, guaranteeing that each copy contains exactly one center. For the complexity, the authors assume the algorithm takes T rounds and calculate the total bits exchanged by Alice and Bob. They show that T log 2n is greater than or equal to Cn, k, thus proving the lower bound for the K-center problem. This result has implications for the design and analysis of distributed algorithms, highlighting the trade-offs between approximation quality, communication complexity, and computational resources. In the context of the K-center clustering problem, Algorithm 3 is presented as a two-approximation algorithm in the CLIQUE model. This algorithm consists of two phases, computing all pairs' shortest distances and greedily finding the centers. The first phase can be performed using known algorithms, either exactly or approximately, with the latter providing faster computation times. The second phase involves K1 iterations, where in each iteration, the furthest node from the current set S is identified and added to it. This process is repeated until S contains K nodes, which are then marked as centers. If exact all pairs' shortest paths are computed in the first phase, the set S computed by the algorithm is a two-approximate solution for K-center, as indicated by lemma 2. However, if only an alpha approximation with one-sided error of all pairs' shortest paths is computed in the first phase, the set S obtained by the algorithm is a 2 alpha approximate solution for the K-center problem, as shown in lemma 4. This extension allows for faster computation times while still maintaining an approximation guarantee. The algorithm's performance is evaluated based on its approximation ratio, which is the ratio of the maximum distance from any node to its closest center in the solution provided by the algorithm to the maximum distance in an optimal solution. An approximation ratio of 2 indicates that the algorithm's solution is within a factor of 2 of the optimal solution. The use of approximate distances in the first phase of the algorithm increases the approximation ratio to 2 alpha, demonstrating the trade-off between computation time and approximation quality. In the proof of lemma 4, it is assumed that n greater than k. If n is less than or equal to k, the algorithm returns all nodes as centers, providing a trivial solution. The set S returned by algorithm 3, the furthest node V from S, and its distance R are considered. It is claimed that opt k is greater than or equal to R, 2 alpha, where opt k represents the optimal solution for the K-center problem. Table 1 in the research paper presents approximation times for the K-center problem within the CLIQUE model, showcasing varying approximation ratios and constants. This table illustrates the trade-off between approximation ratio and time complexity of algorithms. The authors prove that for any constant 0 less than epsilon less than 1, there exists a deterministic algorithm providing a 2 plus epsilon approximation in O, n 0.158 plus k rounds on unweighted graphs, a 4 plus epsilon approximation in O, log 4 lone plus k, rounds on unweighted graphs, and a 6 plus epsilon, approximation in O, log 2n plus k, rounds on weighted graphs. Additionally, they demonstrate the existence of a randomized algorithm yielding an O, lone, approximation in O, k, rounds on both weighted and unweighted graphs. The author's approach is rooted in the observation that in any optimal solution, there exist two nodes in S union, V, that share the same nearest center, with at least one of them having a distance of at least r2 alpha from their common center. This implies that S is a solution with an approximation ratio of at most 2 alpha. The results in Theorem 5 and Table 1 indicate that K center can be approximated in the same time as all pairs' shortest paths computation, up to an additive O, K, time. The paper also notes that for the specific case of 2 plus epsilon approximation, a much faster randomized algorithm exists, running in O, poly log n, rounds. The paper acknowledges contributions from Morteza Menemizada, Mihal Dori, and the anonymous reviewers of Sirocco, 24. Distributed algorithms for graph problems have been extensively studied, with a focus on facility location, shortest paths, and clustering. Superfast distributed algorithms for metric facility location have been developed, emphasizing the need for efficient solutions for large-scale graph problems. Algebraic methods in the congested clique, fast approximate shortest paths, and near-optimal spanners in the congested clique have also been explored. Furthermore, research has been conducted on fair K-center clustering, dynamic algorithms for K-center on graphs, distributed verification, and the hardness of distributed approximation. The literature also covers distributed algorithms for finding triangles and small subgraphs, exponentially faster shortest paths in the congested clique, and the power of the congested clique model. Additionally, a distributed O(1) approximation algorithm for the uniform facility location problem has been proposed. Classic work on clustering to minimize the maximum intercluster distance has also been referenced. This comprehensive review provides a solid foundation for understanding the state-of-the-art in distributed algorithms for graph problems, laying the groundwork for the novel contributions presented in subsequent sections. This study presents a comprehensive analysis of 35 existing datasets related to neural networks and their application in image classification tasks. These datasets were critically evaluated to identify biases, inconsistencies, and limitations, which are crucial for developing robust and generalizable deep learning models. A systematic review of the literature revealed that most existing datasets suffer from issues such as class imbalance, noise, and incomplete annotations. To address these challenges, the researchers proposed a novel framework for dataset augmentation and preprocessing. This framework involves a combination of data normalization, feature scaling, and oversampling of minority classes to improve the overall quality and diversity of the datasets. The study employed a range of evaluation metrics, including accuracy, precision, recall, and F1 score, to assess the performance of different neural network architectures on the preprocessed datasets. The results showed that the proposed framework significantly improved the performance of the models, with an average increase in accuracy of 10% and an average increase in F1 score of 15%. A key finding of the study is that the proposed framework can effectively mitigate the effects of class imbalance and noise in the datasets, leading to more robust and generalizable models. However, the study also acknowledges limitations, such as the need for additional computational resources and the potential for overfitting. Future work involves exploring the application of the proposed framework to other domains, such as natural language processing and speech recognition. Additionally, the researchers plan to investigate the use of transfer learning and domain adaptation techniques to further improve the performance of neural network models on diverse datasets.